Let's start with the same queuing model what we have learned yesterday to continue the queuing model. Starting from slide number 31, illustrate of transient and steady state condition. So you can see over here the NT and ENT, which is shown in this graph, the number of customer in the system at the time t, which is nothing but NT, is showing the zigzag manner, and the red line, which is showing the ENT curve, which is represent the expected number of customer in the system. So you can see the difference. You can see the difference over here. The NT and ENT, the number of customers in the system, and represent the expected number of customer in the system. So this is the graph between. It started with the same, the 10, and moving the NT graph, I mean the NT curve, the number of customer in the system, it may vary. Why it is shown up and down? Because it may vary. Sometimes customer will be more and sometimes customer will be less. So it depends. So that's why it is in zigzag manner, and it is up and down. ENT is represent the expected number of a customer. It is expectation. ENT is nothing but a E. Just keep in mind E stands for expectation. So expected number of a customer. So it maybe go up, maybe go down, maybe go flat. It is expected. The next, it is notation for steady state analysis. Then this is we can say that we have the notation for steady state analysis. The probability that there are exactly n customer or job in the system. The L is the expected number of customers in the system. LQ stands for expected number of customers in the queue. W is expected time a job spent in the system, and WQ is nothing but expected time a job spent in a queue. So these are the notations for each and every value what we can see or what we can check over here. Then birth and death process, I think we have completed this. Now we have to start from here. Assumption a basic queuing process. Infinite calling population. Infinite calling population which is independent between arrivals. There is no dependency between the arrivals. The arrival process in a poison with an expected arrival rate lambda, which is independent of the number of customers currently in the system. The queue configuration is a single queue with the possibly infinite length. No reneging or barking. The queue discipline is FIFO, what I have told you about, first in first out. The service mechanism consists of a single server with exponentially distributed service time. Mu is equal to expected service rate when the server is busy. Then ER of a county hospital. It's an example. So situation, suppose patient arrive according to the poison process with intensity lambda. The time between the arrival and expected mu distributed. The service time, I'm going to say the doctor examination and treatment time for the patient, which is nothing but a service time of the doctor, follows an exponential distribution mean, which is 1 by mu, which is expected distribution mu, which is called mu. So service time is nothing but just like a patient has arrived in a clinic, so doctor will check that particular patient. So from checking to till the doctor has leave that patient, so the time between these, I mean to say when the customer, I mean to say the patient has entered into the clinic and the doctor has started to checking the patient, from that time and when the doctor has released the patient till that time, this is the time. So this is the service time in which doctor will serve the patient, like that. So this is all the service time. The ER can be modeled as a MMC system where C is the number of doctors. So data gathering, lambda is equal to 2 patient per hour and mu is equal to 3 patient per hour. So there is some question, should the capacity be increased from 1 to 2 doctors, and how are the characteristics of the system? I mean to say lambda, WQ, W and LQ and L affected by increase the service capacity. We will see over here summary of the result. of county hospital. It's a name of any hospital like that. We have taken a county hospital. So interpretation: to be in the queue, to be in the waiting room. See, suppose waiting room. Why we are asking the waiting room? See, there when anyone go to the hospital or any doctor clinic, so will be some patient who will be treated by the doctor, and some patient has to wait. Some patient has to be in queue. So they are in queue. So the person who are in queue, they should be waiting in some waiting area. There should be some waiting area in the doctor clinic or a hospital. So the person who is not treated, they have to wait. Whose number will come, they will go to the doctor, and doctor will start treatment. So like that. To be the system, to be in ER waiting or under treatment. So characteristics, what the characteristics were: one doctor and two doctors. So if there is C is equal to 1, so 2 by 3, this is they have given the statistics. So it is warrant or hired a second doctor. Queuing model and system design for one. Design of a queuing system usually involves some kind of capacity decision. What capacity decision? The number of service station, the number of servers per station. So how many service station we have in a where we have a service station, and how many servers are there in per service station. The service time for individual server, the service time, how much time it will take for each and every server, what we have talked yesterday. The corresponding decision variable is lambda c and mu. Example: the number of doctors in the hospital. So it is service station. Doctor is nothing but a service station. The number of exit and cashier in the supermarket, like that example. The choice of a machine type at a new investment decision. The localization of toilets in a new building, etc. These are the examples. So queuing model and design, system design. And system design. Design of a queuing system usually involves some kind of capacity decision. The number of service station, we have done this. The queuing model number 2. Two fundamental questions when designing a system or queuing: which service level should we aim for, and how much capacity should we acquire? So these two questions, it's a fundamental question we have to keep in our mind when we're designing some queuing model. The cost of increased capacity must be balanced against the cost reduction due to the shorter waiting time. Specify a waiting cost or shorter cost acquiring when the customer have to wait or service, or they specify a acceptable service level and minimize the capacity under the condition. The shortage or waiting cost rate is situation dependent, often difficulty to quality. Should reflect the monetary impact a delay has a organization where the queuing system resides. See, actually this is asked about the waiting. How we have to, there should be some waiting cost or not. If the person is waiting, so the waiting cost should be high. Waiting cost in the sense waiting cost here in the sense of time, because there is no cost involved when you are standing on the queue, but obviously the time has been acquired over there. So time is nothing but they have sense as a cost over here. So they have used the word cost. Different shortage cost situation. External customer arrive to the system. Profit organization. The shortage cost is primarily treated to lost revenues, which is nothing but a badwill. Non-profit organization, this shortage cost is related to the shortest cost. Internal customer arrive to the system. The shortest cost is related to the productivity loss and associated with the profit loss. When the productivity will loss, then profit will loss. When anyone is working and his productivity will increase, obviously the profit will increase. If I am working somewhere and my productivity is reduced, so it will impact my organization. If I improve my productivity, my mentor say I will do the productive work if I suppose I have a 9 hours to work in my organization, and in 9 hours, at least 7 to 8 hours, I will do the productive work. So it will give the productivity R. It will measure the productivity R, and according to that, my cost will increase. My mentor say for which I am billable, just like I am billable for some project. So the project cost will increase because I am working for that project at least 8 hours, which is nothing but a productive hours. So my product cost has been increased. So that's why they have used the productive loss. If If the productivity loss, then obviously the profit will lose. But usually it is easier to estimate the shortage cost in a situation 2 than in a situation 1. The analyzing design. This is the design how you can calculate the cost trade-off. There is three term which they have used: TC, SC and WC. WC is expected waiting cost. WC is expected waiting cost. Then SC is expected service cost, and TC is total system cost. So total system cost is nothing but the waiting cost plus service cost. So these two we have to add, then we will get the total cost, which is shown over here. Give a specified short of the waiting cost function analysis, straightforward. So just keep in mind, total cost is nothing but the waiting cost. Waiting cost also involved, because waiting is nothing, just if they want to, just like I have given you the example, if I am in a queue, I want to take one ticket from the reservation counter. So we will calculate how much time it will take to get the ticket in my hand. So it will involve the waiting time for which I am in a queue, that time plus the service time, what the time has been taken by the particular person who gave me ticket. So the waiting time plus service time is equal to total time. The same over here, total cost is equal to waiting cost plus service cost. The analyzing linear waiting cost. The linear waiting cost is nothing but CW, which is nothing but waiting cost per customer and time unit, per customer time unit. So summation of NPN is equal to CW. L is nothing but CWN. CWN is waiting cost per time per unit when N customer is the number of the system. They have shown over here. In previous slide, we have seen the value of L is nothing but summation of NPN probability Poisson distribution from 0 to infinite. Then service cost, we can see over here. Service cost is nothing but C into CS mu. CS mu is expected per cost per service, expected cost per server, and time unit as a function of mu, which is shown over here. So this is, and C is nothing but a number of servers. So we will multiply these two, so we will get the service cost. So total cost is nothing but the service cost and waiting cost. So we will service cost, which is seen over here, C into CS mu plus waiting cost. So waiting cost over here. So we will add these both, as we can see over here. So total cost is equal to waiting cost plus service cost. So we can see that. So total cost is equal to this cost and waiting cost. So these two, when we are going to add, so we will get the total cost. So determining mu and C, both. The number of servers and their speed can be varied. Obviously, server can be varied and their speed sometimes might be because of some issue, server may be down. We have seen a lot of time in the reservation counter, that time the server has been down, so we are not getting ticket at a time, at particular time, or at the time. So the server speed may be down, so it depends on the frequency of the server. I mean to say frequency of the speed of the net, I can say that. Speed can be varied. Usually only a few alternatives are available. So definition over here. Computer procurement. An example, a university is about to lease a supercomputer. There are two alternatives available. The M computer, which is more expensive to lease but also faster. The C computer, which is cheaper but slower. These two type of computer. Processing time and times between jobs arrival are exponential. M and M1 model. So mu is equal to 20 jobs per day. Mu M is equal to 30 jobs per day, and mu C is equal to 25 jobs per day. So these are the jobs per day. The leased and waiting cost. The leasing and waiting cost shown over here, which is CM and CC. CM is nothing but leasing price and CC is equal to nothing but waiting cost over here. So it will shown over here. The waiting cost per job and the time unit is estimated $50 per job per day. So question, which computer should be university choose in order to minimize the expected cost? Then simulation. What exactly the simulation and how it will help us in queuing model? So simulation is experimental with a model mimicking the real world system. Actually, this is nothing but a mimicking. You have might be sometimes you have the listen the words simulation, flight simulation, wind tunnels, etc. This kind of the BPT situation computer based simulation is based on used for analyzing and evaluating complex stochastic systems, just like uncertain service and inter. Basically, simulation is used for inter-arrival times and all the things in the simulation we can utilize where we have a random numbers. With the help of random numbers, we will calculate the I can say that the expected number of uh, I can give you an example. Suppose you have a some cake shop nearby your house and you have to calculate a number of customer arrival in a day. My mind is, so you will take the 30, you will take the data of 30 days. Suppose day one, so 5 days, only 5 days we can start. Suppose day one you have a 10 customers and day two you have a 15, you day three have a 3 customer only, you day four have a you 15 customer, day five is a 50 customer like that. So you gather the data and number of foot pass. Foot pass in the sense number of customers has arrived in the shop. So these two data they will give in the question paper, and they will give you the random number. They will give you the random number. With the help of random number, you will get why what will do with the help of customer. We will use the probability. We will calculate the probability. When you they will give you the probability over here. When you take the probability, then you create the cumulative probability for that. When you create the cumulative probability, and then after that you have to calculate they will give you the random numbers, and you have to check in between which random number the value has rise of the customer. So suppose there is a probability distribution. In the probability they have a 0 0 to so 10 to 15. 10 to 15 you have to check how many customers are there in between 10 to 15. So for that, just like in 10 to 15 there is 10 customers, you have to take that data and put directly into the 10 to 15. So you will get the number of arrival for that particular day. So this is the way we can do, but we will do one question of simulation so you understand more and more. The simulation, why it is, why use it. It's cheaper and less risky than experimental with actual system. This is very much cheap and we can less risky I can say then so that you can actually get the real picture. I can say not real but similar, very similar picture of the data. Simulate creativity since it is easy to test and affect new ideas. It is very easy to test and you will get new ideas for that. A powerful complement to the traditional symbolic and to analytical tool. This is nothing but an analytical tool. You are only analyzing. You are not giving some real data. You have to calculate the foot path. You have to calculate how many customers have come in 5 days, average number of customers. So you are giving the analytical analysis. This is nothing but an analytical analysis through which you are going to give some data kind of thing to the that particular organization like that. So fun tool to work with. This is very funny. You will get it is very much easy and you will do quickly in the simulation. Simulation versus symbolic and analytical tools. So we can see that what is the strength of the simulation. Provide a quantitative measurement, flexible, can handle any kind of complex system and statistical interdependencies, capable of finding inefficiencies otherwise not detected until the system is in operation. What is weakness? Can take a long time to build. Yes. Usually require a substantial amount of data gathering. Obviously there is we require some data so that we have to start our gathering. When we gather data, then only we can do some analysis, otherwise it is not possible. Easy to misrepresent reality and draw faulty conclusions. There may be a chances for this statement. Generally not suitable for optimizing system parameter. A simulation model is primarily descriptive while an optimization model by nature is prescriptive. Modern simulation software packages are breaking compromise, graphical interface, achieve the descriptive benefit of symbolic tools like flowchart and then optimization engines. Building a simulation model. Some general principles to build a simulation model. The system is broken down into suitable components or entities. So we have to broken down the system into suitable components. What we have to initially I have told you about. The entities are modeled separately and are then connected to a model describing the overall system. This is the bottom up approach. There is two approach, bottom up and top down. So we are using basically the bottom up approach. The basic principle apply to all types of simulation model, which is static or dynamic, deterministic or stochastic, discrete or continuous. In BPD, business planning and OMC situations, computer based stochastic, discrete event simulation, example in extend the natural choice, focuses on events affecting the state of the system and skip all intervals in between. So this is the steps of simulation. We will start with the project formulation, set objective, then model conceptualization, data collection, model translation, verified, validating, then experimental design, model run and analysis. These all, then implementation, experimentation, model building, and this is all involved. It's like project definition, start of the project, implementation, and model building over here. Then experimental we are doing there, then implementation we are doing there. So this is kind of project step which we can see here. Then model verification and validation. The slides are there still. I think 3 slides more. Then model verification and validation. So model verification, which is nothing but efficiency, we can see that it is model correction built programmed. It is doing what is intended to do. Then validation, which is effectiveness. This is efficiency and effectiveness. It is the right model build. Does the model adequately describe in reality you want to model? Then does the involved decision makers trust the model? Two of the most important and most challenging issue in performing a simulation is simulation study. Then model verification method. Find alternative ways of describing evaluation the system and compare the result. Simplification enable testing and special cases with predictable outcomes. Removing variable to make the model deterministic. Removing model job types, running the model with one job types. This is not that much important. Validation interactive. We will start with some questions of simulation. We can see over here. Might we will get in. Wait, I will check in because I don't have a question right now with me, so I will try to solve some question over here. Let's see, we will get some question or not. If I will not get over here, so I will bring tomorrow one question and will show you over here. Meanwhile, I will take another slide. Question is not there, I think so. I will bring my book so we can do some practice. At least one question practice we will do. That's sufficient. So at least you can understand the basic knowledge of the simulation, how we will work for this. This is the Hungarian method using simulation. This is not related with us. Forget this. I will bring my own book. So I will start with another topic, which is nothing but assignment problem. We have to start. Assignment problem. What exactly the assignment problem? We have seen that assignment problem is nothing but which is related with method to assignment of the, I mean to say, work. We have seen in the transportation little bit. Why it is not coming over here? Let me check with my So we have assignment problem first. So now start with the assignment problem. Let's start with the assignment problem. What we have seen in the last, when we have started the transportation, we have seen some assignment kind of problem where we have some table kind of scenario in which we need to remove all column and rows with zero with the help of some calculation. We will see some more examples over here in the assignment model. That is nothing but the assignment model which is Hungarian method we have seen over there. In the transportation, we will see over here again. What is the learning objective? So to solve assignment problem with the Hungarian matrix reduction method, it is nothing but a reduction method. It's reduce the each and every column and row. So chapter outline is assigned model approach, unbalanced assignment problem, maximization assignment problem. We will see over here. So assignment model approach, what exactly is the assignment model approach? The special purpose of LP algorithm is the assignment method. Linear programming, LP is nothing but a linear programming algorithm is the assignment method. Each assignment problem has associated with in table or matrix. Some table or matrix is there. So each assignment problem has been associated with some table and matrix. Generally, the row contains the objects or people wish to assign, and the column comprise the task or timings we want them assigned to. The number in the tables. The numbers in the table are the cost associated with each particular assignment. The number in the table are the cost associated with each particular assignment. The Fixit shop has three push objects to repair. They have three repair person with different talents and abilities. Suppose Fixit shop, there is a three repair person with different talents and abilities. The owner has estimated the wage cost for each worker for each object. The owner will. So what exactly the owner will do? Owner will exactly estimate the wage for these three persons. Owner is responsible to estimate the wage for all these three persons for each project. The owner object is to assign the three projects to the workers in a way that will result in the lowest cost to the shop. So what exactly owner will think object is assign the three projects with the three workers in the way the result will be the lowest cost to the shop. It will, I mean to say, the owner will assign the three projects, three work or three jobs to three different people, so that I mean to say the work should be the more to the worker side and less cost for the owner side, like that. Each project will be assigned exclusive to the one worker. This is they have written over here. The estimated object repair cost for a Fixit shop assignment problem. This is like the project. There's 3% which I have asked you about. 3% and 3 project. 3 project and 3%. Person named Adams, Brown and Cooper. So Adams has assigned for first job for $11, second job for $14, and third job for $6. Same for Brown. They have $8, $10, $11, and for the Cooper 9, 12, and 7. This is the 3 jobs or projects which have been assigned to three different persons on these particular cost. Summary of the Fixit shop assignment alternative and cost. There we can see that. So we have what we have done. We have see the project assignment. Just like Adams, Browns, and Cooper. So labor cost for the first job is 11, 10, 17, which is nothing but the total cost 28. Then again Adam, Cooper, or Brown 11, 12, and 11, 34. We have what we have done. We have taken the jobs from here, what we have given, and we have assigned over here all the jobs. You can see that. So we have added each and every job. We have added what we have assigned over here. So first job, Adam, Brown, Cooper. For second job, Brown, Cooper, Adam, Brown. Same with the third. So we have added all these three. All these for the first job, Adam, Brown, and Cooper. We can see that. So 11, 10. For first 11 for this. For second this is 10, and for third Cooper this is 3, 7. So we have added like this. 11, 10, 7. So first, second, third. Then Adam first, Cooper. Then Cooper will go on second. Then we have a first job is same for everyone, but the second and third job we have changes the probability. we have changes over here. For second and third job we added. So we have seen that the total cost over here. So 34 is the maximum total cost has been assigned to Adam, Cooper and Brown for the first, second and third job assignment. So Hungarian method, what the Hungarian method or flood techniques will do? The Hungarian method is an efficient method of finding the optimal solution. It will find the optimal solution to an assignment problem without having to make direct comparison of every option. It will not directly comparison with the every option. It's operate on the principle of matrix reduction. It will be one table or matrix. We have to reduce the matrix by subtracting the particular value. We will see. By subtracting and adding appropriate number in a cost table or matrix, we can reduce the problem of a matrix of opportunity cost. What exactly we are doing? We are getting the opportunity cost while we are adding something to that particular number or reducing that from that particular number. So opportunity cost show the relatively penalty associated with the assigning any person to the project as opposed to making a best assignment. We want a best assignment. We want the optimal solution. For optimal solution, we will either we can add something on that particular number or we can reduce. So we can see that what we need to do. We want to make assignments so that the opportunity cost of each assignment is 0. So steps, there is a 3 steps for assigning method. First find the opportunity cost table. By first do remember we have to find the opportunity cost table by. How we will get? Subtracting the smallest number in each row of the original cost table and matrix from every number in the row. So what we just like there is it is 3 cross 3 matrix. So what we will do, we have to check out if we are going to first column, we have to check what exactly the minimum value of the first row. So what I will do, I will subtract that particular value with each value of that particular column. The same thing we will do in the row side also. So 3 cross 3, each time we have to reduce from 3 column, and the same thing in the 3 row. The subtracting the smallest number in each column of the table, obtaining a part A from every number in the column. Then second step, test the table resulting from step 1 to see whether an optimal assignment can be made or not. We have to check either whether we can make optimal assignment or not by drawing the minimum number of vertical and horizontal straight lines necessary to cover all the zeros in the table. We have to check. We have to make one horizontal line and we have to make one vertical line, and we can see that how many zeros are there while subtracting. When number is subtracting with itself, it will become a 0. So how many zeros? We have to actually cut the maximum number of zeros over there. If the number of lines is less than a number of rows or columns, process to step 3. See, if there is a 3 cross 3 matrix, so we have to see either we can cut 3 row, or my mind is at least 3 row or column. Both. My mind is if we are going to add these, either we are going to cut row wise or either we are going to cut column wise. If there is a 3 cross 3 matrix, so we have to come at least 3 rows or columns. Either 3 rows or either 3 columns, whatever. If that will not happen, then we have to again come and revise a present opportunity cost table. By subtracting the smallest number not covered by the line from every other uncovered number. What we will do? When we are going to cut, at least 1 or 2 line has been cut over there. So in the 3 cross 3 matrix, still suppose I have only 1 row. So still we need to cut either 1 row or 1 column or 2 row or 2 columns, whatever. So for that we will check which is the number which is not has been cut till now, which is the smallest number which is not cut till now. If suppose there is number 4 which is not cut till now and it is the smallest number in the entire matrix, then what? Then leaving the instruction of the horizontal vertical lines, return to step 2 and continue the cycle until the optimal solution is possible. Then what we will do? We will subtract that particular 4 to each and every value which is not cut. So we are going to subtract those values from there. This is a step. So step 1, what we have told with step 2, then if we are not getting optimal the revised opportunity cost table in step 2, then again subtract, then this is all they have written over here. This is the way. Step 1, find the opportunity cost table. We can compute row opportunity cost and column opportunity, which I have told you. Either we have to cut row or we have to cut the column. What we need is the total opportunity cost. We derive this by taking the row opportunity cost and subtract the smallest number in the column from each number in the column. We have to subtract the smallest number with each row or column. This is the same thing. The Hungarian method flood technique. Cost of each project assignment, which is shown where the select project 1, 2, 3, Adam, Brown and Cooper, 11, 14, 6, and the row opportunity cost table. This is second one, 5, 10, 0. See what they have done. We can see that this is the column. First one is the column. You can see that this is the column, first row, column by column. This is the first row. What they have done, they have subtracted from this row, they have subtracted the 6. This is because this is the smallest value. So they have subtracted over here. So you can see that when they have subtracted the 6, you will get here 11 minus 6, 5, 14 minus 6, which is 8, and then 6 minus 6, which is 0. Then again here is 8 is the smallest, then 8 minus 8, 0, 10 minus 8 is 2, 11 minus 8 is 3. Then again 9 minus here is 7 is smallest. So 7 minus 9 is 2, 12 minus 7 is 5, and here 0. So you will see 0, 0, 0. We will get 3 zeros, but still we cannot cut, because to cut that particular column, row or column, we need at least maximum 0, 0 or maximum number of zeros. So all the zeros will come, then we will cut that. The opportunity cost of assigning Cooper to the object 2 is 12 minus 7, which is 5, which is shown over here. The next. So now you can see that this is the same what we have seen over here. So we derive the total opportunity cost by taking the cost of table 29 and subtract the smallest number of each column. Now again what they have done, we can see that there is what is the smallest number in the entire table, entire matrix. We found that 2 is don't take 0, because we need to create column and maximum number of rows or maximum number of columns 0. So don't take 0. 0 is the smallest number, but we have to take apart from 0 some other number, either from which is started from 1. So 2, we have seen that 2 is the smallest number over here. So 2 is the smallest number. So what I will do, again I will subtract each and every row, each and every column with the 2. So when I'm going to subtract 5 from 2, 1 second, what they have done, 2, what happened? So you can see over here, they have subtracted each row over here. Now column, this column has no 0, this mid column has no 0. So what they have done, they have subtracted this column from 2. From here we can see that I have told you each and every column should be comment with each and every. They have eliminated the row over here. They have seen that they have work on the row. So each and every row each and every row has a 0. So you can see this row has a 0, this row has a 0, this row has a 0. Now the same thing we have to apply the column, but in this column we have a 1 0. In this column we don't have any 0, but in this column we have a 2 0. So what again I will do, because this column don't have any 0, so again I will apply the same method over here in the second column. So what I will do, I have to subtract that, because 2 is the smallest number in this column, so I will subtract 2 from each and every value of the column number 2. So from 2 minus 8 is 6, 2 minus 2 is 0, and 2 minus 3, 5 minus 2 is 3. So we will get this another matrix over here. So I have seen that. So now new matrix total opportunity cost table become 5, 6, 0, 0, 0, 3 and 2, 3, 0. Now next. Now test for the optimal assignment. We want to assign workers to project in such a way that total labor costs are at the minimum. We would like to have a total assigned opportunity cost is 0. The test to determine if we have reached an optimal solution is simple. We have to find the minimum number of straight lines necessary to cover all the zeros in the table. If the number of lines equal to the number of columns, an optimal solution has been reached. So number of line has to be equal to number of columns. So we can see that. So if you see that in the second line we have a number of zeros, maximum number of zeros. We have a 2 zeros over here, and in the first column, second row we have a 2 zero, and first third column we have a 2 zeros. So 2 zeros, this is cut, this is cut. So we require only 2 lines to cover the zeros, and the solution is not out. This require only 2 lines to cover the zeros. So the solution is not optimal. Revise the opportunity cost table. We subtract the smallest number not covered in the straight line, all numbers not covered by the straight line. The same number is added to every number lying at the intersection of the 2 lines. When we return to step 2 to test the new table, again what they have done. So what they have done, we have seen over here. So initially the column was 5, 6, 0, 0, 0. So this column has been cut and this row has been cut. After cutting this, we have found that 2 is a minimum number over here. So what I will do, I will subtract the remaining value, I mean to say 5, 6, 2, 3 with subtract with 2. So what is the new number has been come over here? So it will come over here like, so 2 was here. So 2 minus 5 is 3, 2 minus 8, 6 was here, 4, and what this has to be same, and this 3 was here. So 3 minus 2 is 1. So we will get this new value. So here we can see that the maximum number of rows we will get from here, from here, or from here. This is the 3 column has been cut over here. So we can see that 3 column has been cut, first, second, and third. So covering line 2, line 3, and line 1 over here. So this requires 3 lines to cover the zeros so that the solution is optimal. Why we have cut 3 lines? Why we have not cut the 2 lines from where we will get the optimal? Why we not get the optimal solution over here? Why? Because in the course, because there is one rule in the Hungarian method. Because this is the 3 cross 3 matrix, 3 rows and 3 columns. So we need at least 3 lines should be cut, because 2 line has been cut over here. So again we have to work on that, and we have to cut at least 3 lines in the 3 cross 3 matrix. If n is equal to 3, because 3 cross 3 matrix, so we have to cut at least 3 lines either row or by column. So this requires 3 lines to cover the zero so that the solution is now become the optimal. So making the final assignment, the optimal of the assignment in Adams to project 3, Brown to project 2, and Cooper to project 1. But this is a simple problem. For larger problem, one approach to making the final assignment is to select a row or column that contains only 1 zero. Make the assignment so that cell and rule out this row and column. Follow the same approach for all the remaining cells. So what they have given over here, 3, 2, 1. So Adam for project 3, what they have written, Adam for project 3, Brown for project 2, and Cooper for project 1. So we will add this. Adam for project 3 cost is 6, Brown for project 2 cost is 10, and Cooper for project 1 is cost is 9. So total cost becomes 25. So this is the total labor cost, $25, through which we will get something. See, this is the final assignment. So you can see that you have seen over here making the final assignment. So first assignment 340, we have assigned 0 over here, then we have assigned 0 0 over here, then after that we have assigned 0 0 over here. So first, second and third, there is no need for this unbalanced problem. Unbalanced assignment problem. Often the number of people or object to be assigned does not equal to the number of tasks or clients or machine listed in the column, and the problem is unbalanced. Unbalanced in this is matrix of 2 cross 3 or 4 cross 3, like that. This is the unbalanced problem. When this occurs, there are more rows and columns. Simply add a dummy column or task. If the number of tasks exceeded the number of people available, then we add a dummy row. Since the dummy task or person is non-existent, we enter 0 in its row or column, as the cost or time should be estimate. So you can see that here the 4 cross 4, 1 2 3. So in the previous one we have seen that it is a 3 cross 3 matrix, but they have added one more worker, which is Davis, over here in the 4th row. Initially we have Adam, Brown and Cook, but now they have added Davis over here. So Davis, they have again 3 jobs, but they don't have any another 4th job for this Davis. So what they have done, they have added one dummy task over here, dummy project, and they put 0 0 0. What they have written over there, 0 0 0 they have added. To fix its shop has another worker available. The shop owner still has some basic problem for assigning workers to the project. So, but the problem now needs a dummy column to balance the 4 workers and 3 projects. So some assignment problem has phrase in terms of pay, maximizing the pay of profit or effectiveness. It is easy to obtain an equivalent minimization problem by covering all the numbers in the table to opportunity cost. This is brought about by subtracting even every number in the original payoff table from the largest single number in the table. Transformed entries represent opportunity cost. Once the optimal assignment has been found, the total payoff is found by adding the original payoff of those cells that are in the optimal assignment. The British Navy wishes to assign 4 ships to patrol 4 sectors in the North Sea. Ships are related to their probable efficiency in each sector. The commander wants to determine patrol assignment producing the greatest overall efficiency. This is given, they have given the example. So 4 ships, 4 sectors. Opportunity cost of the British shop. First, convert the maximum efficiency label into the minimizing opportunity cost table by subtracting each rating from 100, the largest rating in the whole table. This is the maximization problem. So we have seen that what exactly the largest rating of the whole table. The smallest number of each row is subtracted from every number in that row, and the smallest number of each column is subtracted for every number in that column. The minimum number of lines needed to cover the 0 in the table is 4, so this represents the optimal solution, which is we know. So ship 1 to sector D 50. So they have calculated the efficiency after they have done. So we have done with the maximization assignment problem here. So we have done with the assignment problem now, which is very easy. Hope you understand, because this is one of the easiest problem ever have been seen in quantitative techniques. One of the easiest problem. You don't need to do anything. You need to only apply. You only need to subtract the smallest value from column and from the row. When you subtract the smallest value from the column and from the row, you will get the number of zeros. When you get the number of zeros, I meant to say equal to the matrix, you need to cut, that is your optimal solution. And where you get the zero, you have to add, take that number from original column and you have to add those number and you will get the final cost. That's it. This is one of the easiest problem I have ever seen in the assignment problem, one of the easiest problem. So we have done with the assignment problem. Now the few topics has been remaining: time analysis, and one more is decision theory. Decision theory we have time analysis, we have simulation, and one or two more chapters. So almost we will try to complete this. Today's Wednesday, Thursday, Friday, and Saturday. We have 3 days over here, so we will try to cover it out as soon as possible. So we will try to cover it out 4 more chapter in these days. So we have done with the assignment problem now. So now we have 2 more. Hungarian method we have done, assignment we have done. Now we have a decision theory and time series, and decision theory and time series. These two we have. That's it. So we will complete it out tomorrow. Might be decision theory, and day after tomorrow we will complete it out time series. What is not downloading here? Every time reading program